Ciao amici, welcome to a new Amazing Max video tutorial. In this one we are going to talk about my latest patch, the image to particles patch, which basically takes an image and using the GL3 package transforms it into basically a particle system, and then with which we can then play around, so we can reach this kind of effect. Let's maybe go full screen, and we will talk about how to create this effect basically from scratch. So this is the final effect, or at least a variation of the final effect that you can always modify at your liking, of course. So let's start and let's see how we can do that. Alright, so here we are, and let's start. First things first, we are going to need our JIT world. Let's actually create it from scratch. So JIT world. I will often glance up there because this is where my patch is, so I can look at it and kind of not get lost in this madness. So let's call this world, let's call the context, let's call it, I never know how to call the contexts, so let's maybe call it just GTX, cool, like in the kind of Second 74 style. And then let's give it, yeah, of course, let's give it FSAA for the anti-aliasing. Let's give it, I don't know, a window position, a starting window position. Let's give it maybe some window size, so just size 320 by 240. What else? Of course, floating 1. And let's give it FPS, desired FPS, let's say 120, which will only work if your screen has a 120 FPS frame rate refresh rate. Otherwise, you will have to set sync to 0, otherwise we can just set 60 frames per second, but I will set 120. And then let's see what else. Oh yeah, sure, erase color to get a black background. Okay, and then let's activate these with a toggle. We actually maybe also want to have the orthogonal projection too, because we don't want to use the depth, since we're only working with images, and even if these particles are in a 3D world, we actually don't use the depth of the 3D world, we just use the X and Y axis. And we do that because in this way we can have the coordinates of the mouse, we can have them mapping exactly to the coordinates of the 3D world, okay? So we say orthogonal projection 2, right? And okay, then of course we need to be inside GL3, so you go in the preferences, choose your OpenGL engine to GL3, and set it to GL3. If you don't have the GL3 package, you have to download it here from the package manager. So easy peasy, just download it and then you're ready to go. You have probably to restart Max. Now, what we need to create is, of course, we need a system to import our images inside the patch, okay? So we will do something like this. First, let's create a JIT matrix. We will load our image inside this matrix. We can load the image inside matrix using the import movie message. And let's attach it here. Now we need also to get the dimensions of this image that we are importing. So let's do something like this. Let's say trigger be get dim, so to get the dimensions of this image, and then the list containing the matrix. So we will do like this. Create another matrix here. So the first matrix is just to load the image, okay? Then we send the image into another matrix, from which then we can take the dimensions of the image that we loaded, okay? So we can do something like this, root dimensions, and let's put this here. let's check with a message box the dimensions of the image we get. And then we need to set him the send to this matrix the get dim message, and then a bang to output the matrix. So let's make a little test. Let's import an image. So I downloaded these some couple of images here. They all have a background. So I've imported, and of course I need to send a bangles to this matrix. All right. So, okay, we know that this image is 2048 pixel by 2048 pixel. So it's a square image, basically. You know what? We actually don't even need this matrix. I was just being silly. We actually don't need this matrix. We just need the import movie message, which will, and this trigger, which will send the import movie message to this matrix, will send the get dim message, so we get the dimensions, and then bang out this matrix. Now we need another matrix to which we will actually give the type of float32 and some arbitrary dimensions. Now this matrix here is actually of type char, because by default every image we import will be contained in a matrix of type char, but we want actually to have a matrix of type float32 for reasons that we're going to see in a second. So we need actually to connect it like this. But if we will just do this, once we import an image, this will go also, this would actually remain to type float32. I thought this would go to type char. No, okay, it actually doesn't adapt, but just for to be sure, let's give it a type the attribute adapt 0. Okay, now we need to manually set the dimensions of this matrix, because this matrix will not adapt. Its dimensions will always be 100 by 100. So let's actually prepend dimension here, and let's connect these here to give it the dimension of the actual dimensions of the image that we imported. So I made all of this just to have a matrix that has an output of float32. Maybe this could have been done in a better way. I'm not sure. Actually, this is it's kind of okay. Then, so what I've done in my patch is to basically use all images with a black background, because we are actually filtering out the background, okay, if it's black. So I've done this using JIT-gen. That's why we actually want a matrix float32, because we want to go inside JIT-gen. So inside JIT-gen, I've just made a little filter thing, because what will come out of this JIT-gen must be two outputs. One output with the actual colors of the image, and another output with 1 or 0, according to if the matrix, if the color or the pixel has black or not. Okay, so if the pixel is black, it will output a 0. If the pixel is not black, it will output a 1. So we need this because we will use the X-ray object, xray.jit.cellCards, which will actually give us the coordinates of all the cells that have a 1 as a value of the pixels. So we connect this here basically, and then we can use those coordinates to use the xray.jit.cellValue object, which will basically sample those pixels from the actual image, and those only. So we will not have all the coordinates of the black pixels also, but only the coordinates of the pixels that are not black. Okay, so this is thanks to the xray.jit object. Now, if you type xray.jit and this object is just red, it means that you don't have the X-ray package, which you have to download from the package manager. So you just go here, you look for the X-ray package, it's one of those, and then you install it. Alright. Now, let me check. We want to give it, we want to say check at the plane 0, even if it's not so important. And we want to tell it out mode 1, which means will give us float numbers as an output. So let's make a little test. And of course we first have to fill the JIT_gen. So let's go inside the JIT_gen and say, first of all, let's just pass the image as it is. So let's actually, since we already imported the image, we can just keep on banging on this matrix. Oh, sorry, attached it to the wrong output. I wanted to connect this here, right. Okay. So we got the mouse. Okay, this looks good. So let's do like this. Let's switch red, green, and blue. We don't care about the alpha because the alpha is anyway always 1. And then let's sum all these values together. Okay. So if these values are greater than, let's say, 0.02, you can also just say if they're greater than 0, but then we would get also very, very gray pixels. So let's put the threshold a bit higher to 0.02. And this will give us 1 if the pixels are not black, basically. So let's check it out with another GPU window. Let's bang here. Okay, right. So we get a 1 for all the pixels that are actually not black. Cool, because then the JIT-Ray cell cards can actually use those pixels to give us the coordinates, and then the JIT-Ray X-ray JIT cell value will give us the colors for all those coordinates. So it will just put them inside a one-dimensional matrix. Okay, so this is not anymore a two-dimensional matrix. This is a one-dimensional matrix which contains all the pixels that actually are not black. So this is actually pretty useful for us because we don't care about all the pixels that are black. We only care about the pixels with colors. So this is what the X-ray JIT cell card and cell value will give us. That's pretty neat. Okay, now let's go on the left side and let's start to create some GGL buffer objects. So let's create the first one, GGL buffer object. So these will be our buffers that reside on the GPU and basically keep on cycling their output to their input. So this will be our transform feedback. So GGL buffer, and let's give it a type. This will be the position buffer. So inside the GGL mesh, this will actually take the place of the position buffer. Let's give it a name. So out name, let's call it O position, right? Or as an output. Let's create then another one. Let's actually zoom a bit out. Let's bring this guy a bit more on the right, and these. Okay, so this will be our normal buffer. So let's call it output velocity. This will be the velocity of our particles that we output at every frame. Then we need another buffer. Let's use the color buffer for that because this will actually be the color of our particles. So type color, let's call it out color. And then we need even another buffer. So let's call these vertex, let's use a vertex attr buffer. So vertex attributes buffers are basically, I don't know if there is a limit on them, but you can actually just go on and call them vertex attribute 0, 0, 1, 2, 3, and 4, and so on. So, but if you are just one, you can just call it vertex attr. So the vertex attr, let's call it output orig pos, or actually pos orig. So this will be the original position of the coordinates, basically. This will use this to attract back the particles to their original position when we displace them. Okay, so let's start to fill those buffers with some matrices. So in the position buffer, we need to send our coordinates, but the X-ray JIT cell card will send out a matrix that is actually only 2 planes, because the coordinates are just 2 planes, right? X and Y. So let's see, planes is only 2 planes, right? So we actually need a matrix with 3 planes. So let's create a matrix with 3 planes, 3 float 32. Let's say the dimensions 1001, because now we are working with one-dimensional matrices. Let's say adapt 0, because we don't want these to adapt and become 2 planes. Let's connect these here. And inside this matrix, we need actually to send this matrix, the coordinates matrix. So in order to work with these coordinates inside our shader, we need actually to transform these into a 3 planes matrix. Okay, so we can just send this matrix inside this other one, but first we need to get actually the dimensions of this matrix in order to change then the dimensions of this other matrix here. Okay, so we have to create kind of a dummy matrix. Let's do that. Jit matrix. Let's connect this here. Let's actually use a trigger to kind of make fast the order of operations here. So you can delete that. So first we send the matrix to the Jit matrix. Then we actually send it the get dim message, as we did before. We root dim. Even though if it's actually not necessary, we can actually, but we could just say, okay, use this dimension to change the dimension of the other one, but let's just be super neat and root dim in order to not risk that this matrix sends out some other messages. It's a bit unnecessary, but okay. So now that we have the dim, we can say send coords dim, and we can receive it here. So this will set the dimensions of this matrix, and then we actually have to send the actual matrix to it. We can do like this, and coords mat, and we receive these here after we sent the dimensions. So let's visualize everything, if everything works, using a couple of P windows. So let's connect these here and let's take a look. Right, the coordinates basically go from 0. Oh no, the coordinates are actually in an actually pixel coordinates. So we need to divide these coordinates. So we can also take a look with the cell block. So the coordinates, actually cell block is a bit buggy in this case, doesn't visualize everything. But basically the coordinates will go from 0 to, so let's write it down. Coordinates will go from 0 to 2047, I think, because the dimension of this image are, the dimensions of this image are 2048 by 2048. So the coordinates will go from 0 to 2047, right? So let's do this. Before sending this inside the buffer, we actually need to remap those coordinates, right? So let's do like this. Let's go inside JitGen, and we can actually scale. So this that comes, and then we need actually a parameter to use as our coordinates. So dimension x, dimension x. Let's give it a dummy value of 1, and then dimension y. Let's give it a dummy value of 1. So we have to say they go from 0. Yeah, okay, this kind of works. Is a bit. Let's actually do it another way. Let's just do like this: switch x, and then switch y, and then divide the x by dim x, and the y by dim y. Now will go from 0 to 1 on x and the y, right? Then we actually want this to go between -1 and 1, not 0 and 1. So what we do is basically multiply by 2, or we can actually scale 0, 1, -1, 1. Okay, so for the x, for the y. And let's create a vector with 3 components, and we just want to fill the x and the y. Okay, cool. So now we need basically to send this parameter, dmx and dmy, to the actual JIT_gen object. So let's do like this. Let's do here like send image dims, and then let's receive them here. Let's unpack them. It will be 2 integers. And let's say here dim x $1 for the x, and dim epsilon $1 for the epsilon. Okay, and cool. One more thing is that we actually don't want them to go between -1 and 1, because otherwise the proportions of the image will be wrong. So the x, so to maintain the proportions of the image correct, because let's say the image was 1920 by 1080, if we scale both between -1 and 1, then the x will be misproportioned in regard to the epsilon, right? So we need to multiply the x by the ratio of the image, right? So we get the ratio by dividing the x by the epsilon, multiply this, the x by the ratio. Okay, so that's it. We can now check that our coordinates are kind of correct. Right. For some reason I was waiting for a 2-dimensional matrix, but of course this is a 1-dimensional matrix. You can actually just try to take a look with cell block. Ping. Yeah, they will actually go. It's a bit buggy with cell block for some reason. But okay, I actually think that these coordinates are correct, because they go from -1 to 1. They don't have to be in order, because this is just the coordinates of every single pixel. They don't need to be in order from ratio to ratio and so on, right? So let's just trust that this works. So good, we actually got the coordinates from which our particles will start. And also actually these are the original position coordinates, which we will use also later for to get the particles attracted to their original position. So we can send the same matrix also to this buffer here. Cool, let's now create the GGL transform feedback. So TF, we need 4 inputs, since we have 4 buffers. Let's give it the name of a shader, sorry. Let's say shader, my shader, which doesn't exist yet. So we are going to create it in no time. Let's connect these guys like that. Oh, let's now fill the other buffers. Now the color buffer is of course the matrix that comes out from here, right? So let's connect these to the color buffer. Cool. Now the velocity, we want to start with a velocity of 0. So we simply can send inside a matrix, an empty matrix. So JIT.matrix3 float 32 1001, and so let's give it the dimensions of our coordinates, because this is basically the dimensions we are working with. And let's send then a bang in order to output this matrix. So something like this. List the coordinates and then a bang. Alright, we are set. I think we are set. So let's now create our GGL mesh. So GGL mesh GTX cool. And of course, and let's say draw mode points, since we're working with particles. So let's actually say shader, my shader. Right, then color 1. Anyway, going to replace the color. And that's it. Let's maybe give it also anti-alias 1, which should make the points a bit... in GL2 it makes the points from little squares to little circles. Not sure it's the same for GL3, but let's just give it. Okay, cool. That's it. Let's now create our shader object. So JIT GL shader. GTX, oops, GTX cool, name my shader, okay, file, my shader.jxs this time, cool, let's try to open it. Alright, let's save it as this with the name that we gave it, so my shader.jxs, save as all files, right, so save. Cool, so this is now our shader. Okay, we don't need a lot of the things inside here. So as in the previous tutorial when we did the particles with GL3, we want to basically delete all of this stuff. And yeah, we want to basically just to keep a few things. So let's start to delete some stuff that we don't need. More uniform projection matrix we don't need. We don't need at all the projection, the geometry shader. We don't need this at all, right? We don't need this. We don't need that. We don't even need this. So let me check if I made some mistakes, if I deleted too much, or it's actually correct. Looks actually correct. So let's see what we actually need. Now we need, let's call our position, let's call it I position, so input position, vector state position, that's right. Then this will be I color, will be vector state color. Let's create another one, so param name equal I velocity. So we are now declaring basically our buffers that we are inputting inside the transform feedback. We are declaring them inside the shader that we will use to work on the transform feedback. So state velocity, no sorry, this was the normal. Okay, let's maybe change editor, then I can zoom in. Let's open it with Visual Studio Code, plain text, not GLSL. Okay, cool. Now we can kind of have it bigger, zoom in. Okay, so yeah, we are, I actually recognize that this is disconnected. This should actually be connected, so X-ray G cell card should be actually connected to the cell value one. Cool, let's actually connect also git.fps GUI here just to check our frame rate, check that we are not doing anything that is breaking the patch. Okay, looks good. Let's go back to our code. Cool. So we were adding our buffers to the shaders. So let's write here I position. This will be I velocity, all to the vertex program, of course, because this is transform feedback shader, so we don't need to deal with the fragment shader basically. Okay, then let's see another one, param name, let's call it I pos orig. Type, this will be a vec3 state, and we write vertex attr because this is the vertex attribute buffer, right? Let's go here, let's just copy these two ones, let's pass them. So this will be I color and this will be I pos orig. Nice. And okay, cool, let's rename them also here. So I position, right, I velocity in vec4, no, this was a vec3, I velocity in vec4, this is going to be I color, and then another in vec3 I orig, I pos orig, right, okay, cool. Now we also need to set the out, because otherwise the transfer feedback will not work. So we have to say out vec3 O position, because that's the name that we gave to our buffer, right? Yeah, O position, O velocity, O color, O pos orig. So O position, then out vec3 O velocity, so O as output, out vec4 O color, and out vec4 O pos orig. All right. Now let's just visualize our image as particles. So we don't do any particle motion, we just visualize the image as particles. Let's do that. So we just want to say O position equal to I position. O velocity, it's equal to I velocity, which will be 0. O color will be equal to input color. And O pos orange will be equal to E pos orange. Okay, this should already work. Let's check if this actually works. Oh, I'm getting an error. What is it? Assignment of incompatible types. Did I mess something up? Did I mess something up here? So, a bit of time later, I actually found the error. So the problem was that I've called this, I said this was a back 4, which is actually a back 3. Then there was another major error in the patch itself. It was that I gave to the GGL mesh the shader. So I said shader, my shader, which is actually completely wrong because GGL mesh doesn't need the shader. It's only the GGLTF object that needs the shader, because the GGL mesh is just going to be rendered normally without any shader applied to it. All these vertices and all these internal buffers are going to be changed by the shader, right? So now if we click on it, so if we import an image, will be represented as particles. Now, as you can see, there's something wrong here. The image is basically upside down and also red. Now, why is that? The upside down part we can easily correct here by maybe we can even correct it here. No, we need to correct it here. So inside the GGen, we need to sample this matrix by reversing the epsilon. So we will do that like this, using a sample object. We will use a norm, and then we will switch x and switch the epsilon, and then we will reverse the epsilon by subtracting epsilon to 1, and then we use we create again a vector 2 and use this as coordinates. So we connect everything to this sample object, the input to the sample. So now when we bang again, exactly, it's reversed. Instead, the red color is because this is a matrix and it goes to fill a texture. So a matrix, as you know, is in alpha, the orders of the channel in a matrix, the order of the color channels in a matrix are alpha, red, green, and blue, while actually on a texture they are red, green, blue, and alpha, right? So that's the matrix order. That's the texture order. Oops. So we need to, basically, we need a matrix. Git.matrix. With 4 planes, float 32, let's say 1000 by 1, let's say even depth 0. And then let's say plane map 1, 2, 3, and 0. So we put actually the alpha at the last position, like it's organized inside the texture. So let's connect this here, and let's connect this to that. And let's first, we also need to give it the dimensions. So let's do like this, chords dim. Right, from here, we can actually do this very easily. So let's try if I bang now. No, actually, let's import the matrix again. And right, so now it is actually correct. It should be correct. It should be correct. So why is this cut? Why is the image cut? Okay, actually there was no error. I just recreated the GGL mesh and everything went well. So all is well what ends well, I suppose. Let's actually put me here back on the left. This makes much more sense, doesn't it? Right. So, okay. Now we can start to work on our particle system. Or maybe we should save that for another tutorial, since we are already running a bit quite long, I think. Yeah, let's save that for the next tutorial, which I will upload as soon as possible, probably tomorrow. And so yeah, for the moment we have got this setup in which we get an image, we transform it into particles and give every particle a color. So these are just points, basically. If we choose another draw mode, for example, for the GGL mesh, we can see that these are just basically points inside this mesh. So in the next video, we will see how to write the shader to transform our image into a full-fledged particle system. Okay, so how do you say stay tuned? And you can already download the final patch on my Patreon. So if you want, check it out. You can also support me and support my tutorials. Anyway, see you in the next video. Thank you for following, and yeah, see you soon. Ciao.